Hello, now let us see what circle criterion is using some graphical means. Okay, so we will see like how we can utilize the GS itself if GS is connected to a nonlinearity of NL, then how GS can be used for analyzing the stability of a the whole nonlinear system. Okay, so now we saw that using the feedback loop transformations, we saw that if the nonlinearity is in the zero infinity sector, we can say that the nonlinearity is passive, and if GS is also passive, or if it means that if GS is also strictly positive real, then the whole feedback connected system is asymptotically stable. Okay, now if we take the general case such that if the nonlinearity lies within the sector K1 and K2, what we had done was we had rearranged the nonlinearity from the K1 K2 sector. We tried to make it to the zero infinity sector and see what changes or what arrangements we had to do on G of S so that whole system should be asymptotically stable. Okay, so what we did was we did some loop transformations on the nonlinear system, and finally we came up with the G of S, which is this is the whole G of S, new G of S, which says that if 1 plus K2 into GS divided by 1 plus K1 into GS is a strictly positive real function, then we can say that if we have a nonlinearity which lies within this sector, then the whole system is asymptotically stable. Okay, so what does this say? It says that once again we can say that for any system which has a nonlinearity connected to a plan G of S, as if connected to a plan G of S, to check the stability of the system, what we have to check is we have to go and check whether 1 plus K2 into GS divided by 1 plus K1 into GS is strictly positive real. This was what we had seen. Okay, so this theorem is in fact for the general case where we have, this is not 1, it is actually I here, I. So this is the general case for a multivariable circle criterion. So now if we consider the scalar case, this boils down to a graphical representation. We can use graphical representations to analyze the system. Okay, so now we will see when the P is equal to 1. That means we are having, that means unit input and unit output. Okay, U and Y. So we have the scalar case, that is Uy should be greater than or equal to 0 for the system to be passive. Okay, so let us see that. Okay, so using graphical representation, what we can see is we can directly use G of S instead of converting it into this transfer function. We can directly use G of S or the Nyquist plot of G of S to check the stability of the whole closed loop system. Okay, so we will see that. Okay, now okay, so now G of S is given, G of S is given here, and if it is being fed back using some gain K like this. Okay, so what we had seen, what was our problem here? Our problem is G of S is fed back through a nonlinearity here, and this nonlinearity is lying within the sector K1 and K2. Okay, sector K1 and K2, K1 and K2. Okay, this nonlinearity phi of t comma y lies within the sector K1 and K2. So we want to check the stability of the whole system. Now if I have some K lying between K1 and K2, so I have some K which lies between K1 and K2. So let me draw this K1, this is K1 and K2 here, the same K1 and K2 here, and this is the K that I have drawn here for the linear case. This K, let it lie between K1 and K2. Okay, so how, if you are having this linear curve lying connected, a linear system, for this linear system, how do we assess the stability using Nyquist criteria? So the idea is, if what does the Nyquist criteria say? If GS is Hurwitz, that means if GS does not have any poles on the right of the imaginary axis, then the Nyquist plot should not encircle the minus 1 by k point. Okay, should not encircle it, so that Z would be equal to 0. So what is the relation? N is equal to Z minus P. If P is equal to 0, then N should also be equal to 0, so that Z becomes 0. Okay, so that is what we should have. Z is the number of closed loop poles of the closed loop poles of the whole system. That means Z is the poles of GS by 1 plus k into G of S. Okay, in order to have Z equal to 0, if GS is stable or Hurwitz, then P is equal to 0. In that case, the number of encirclements should be equal to 0. Now, if P not equal to 0, if P equal to 0. Okay, if P not equal to 0, what will be then? That means if P not equal to 0 means there will be poles on the right of the imaginary axis of G of S. Okay, if there are poles on the right of the imaginary axis, then what does Nyquist criteria say? Then there should be P number of counterclockwise encirclements about the minus 1 by k point. Okay, there should be P number of, or we can say that if P is equal to M, if P is equal to M, then there should be M encirclements and counterclockwise encirclement. That is important. Counterclockwise encirclements about minus 1 by k point. Okay, this is what the Nyquist plot says that. Okay, now if this k, it lies between K1 and K2. So where does K1 and K2 lie on the GJ omega plane? So this is GJ omega plane. So this is a real GJ omega and this is imaginary GJ omega. So I am only writing IM and RE. So if this is K1, this would be minus 1 by K2, right? Because K2 is greater than K1. So I have minus 1 by K2 near to the 0 point, and this would be minus 1 by K1. Okay, so where would be K? This K would be somewhere here. Between these 2 points should be somewhere here. Like this is minus 1 by K. So if I move K from this point to this point, what happens is that it would be something like this, the whole area, right? It will be the whole area. Okay, so that is the idea that we can use here to analyze the stability of this nonlinear system. But since if K was linear, we could have said that the GJ omega curve should not encircle this whole region, right? Whole region or whole path. Okay, but since K is not linear, we have another way of analyzing the stability of the system. So what does from the feedback condition, what did we get? We got that if for the nonlinearity lying within this sector, what we had to check? We had to go and check for some G hat of S which is positive real. That means 1 plus K2 into G of S divided by 1 plus K1 into G of S should be positive, is strictly positive real. Strictly positive real. So we will try to translate this to the graphical representation. Okay, and then we will get something of this form. That means the curve should not encircle this some region, so that this whole system is asymptotically stable. So we will come to that here. Now if so what is our requirement? We require that the real part of 1 plus K2 into GS divided by 1 plus K1 into G of S should be greater than 0 for asymptotic stability of the system for psi of t comma y lying within the sector M K1 to K2. Okay, K1 to K2. So now how do we translate it here? So what does it say? Let me write it in some form. That means this is in fact a real part of 1 by K2 plus since k1 and k2 here are positive, so k2 by even if I take k2 by k1, we are not taking it here, so it would be g of s, or we have to write in terms of gj omega. Actually it is g, not g of s here, gj omega for all omega element of minus infinity to infinity. Okay, so okay, that's it. So 1 by k2 by 1 by k1 plus gj omega. So this real part has to be greater than 0. Okay, for all omega element of minus infinity to infinity. Okay, is that fine? Now let us translate it to the gj omega plane here. So this is minus 1 by k2 and this is minus 1 by k1 here, and let this be some plot of gj omega. Like this is some gj omega here, it is going somewhere, so this is gj omega, some plot gj omega. So this is g of j omega. Okay, this is real part and this is imaginary part. Okay, so now let us see what does this equation say. Real part of this whole part greater than 0 means that the plot of this curve of or this system should lie to the right of this line, right of this y line. Okay, if I have to lie to the right of this y line, it means that the angle extended by this system should lie between, okay, it should lie between these two lines. Okay, so let us see how it is possible. So let us look at this curve here. Here I will draw with red color, or yeah. Okay, so this any point, so for some value of omega, this is g at some omega 0, some value of omega, let it be g at some omega 0 here. So I got some omega 0, so plus 1 by k2. So plus 1 by k2 would be this length plus this length. Okay, so 1 by k2 plus gj omega, this is minus 1 by k2 plus gj omega, so the length would be this length. Okay, so this would be that length. Similarly 1 by k1 plus gj omega would be this length. Okay, so any on any omega on the whole minus infinity to omega region or domain, we can say that this length is this length and this length is this length. Okay, so now we will see what is this is the magnitudes. This magnitude divided by this magnitude will give the magnitude of the whole system. Okay, so now what is the angle here? So where the whole let this be A, so this would be A divided by B, angle of theta 1 minus theta 2. So this is theta 1 and this is theta 2. So depending upon, so A by B would be a magnitude of this curve of the system divided by this angle. This angle should lie between minus pi by 2 to plus pi by 2. So we will go and look at it. What says that if my omega 0 was somewhere circle, then the angle between theta 1 minus theta 2 would be exactly equal to 90 degree. Okay, that means theta 1 minus theta 2 would be equal to 90 degree. That you can go and verify, because this angle plus this angle would be 90 degree. So theta 1 minus theta 2 would definitely be equal to 90 degree. So if the gj lies between these two sectors, that is k1 and k2, so this is not k2, this is k1 here, so I have done it as k2 here, sorry, this is k1 here. So this is a circle which formed between the k1 and k2 sectors here. So the angle formed by theta 1 minus theta 2 definitely will be equal to 90 degree. Okay, so that means that if the curve is outside this circle or outside this disk which is formed by disk formed by K1 and K2, then the angle would be less than 90 degree, and if this curve is inside this circle, if I have a Gj omega inside this circle, then this function would cause the angle to be greater than 90 degrees, because if I try to take an angle here, this point and this point, definitely I take from the positive real axis, this would be theta 1 and this would be theta 2. So theta 1 minus theta 2 would not lie within this. It would be greater than 90 degree. Okay, plus or minus 90 degree. So that is why from that analysis we can come to the conclusion that if for any Gj omega, if we consider a disk with disk K1 and K2 with the center which forms between these center of these 2 points, okay, with the center of these 2 points, and the radius would be half of this length, okay, then the Gj omega curve, that means the Nyquist plot of Gj omega should not encircle this disk. If the Gj omega Nyquist plot should not encircle this disk if Gj omega is Hurwitz. Okay, the same analysis. If Gj omega is Hurwitz, that means if Gj omega is having no poles on the right of the imaginary axis, that means if Gj omega is stable, then for the whole systems to be stable, the system Gj omega should not encircle the disk. Okay, should not encircle the disk. Now if Gj omega is having poles on the right of the imaginary axis, is having Pm, then this Gj omega should encircle the disk m times in the counterclockwise direction. Then only the system would be stable. Okay, so this is about the asymptotic stability of a system. That means this region is in fact the forbidden region. That means it should, if I have some Gj omega with some poles on the right of the imaginary axis, then that curve should encircle this curve in the counterclockwise direction. Okay, it should encircle in the counterclockwise direction. Okay. So if I have how many encirclements are there for the system? This is one encirclement, and then 2, 1 and then 2 encirclements. 2 encirclements are there. So then if P is equal to 2 for this case, then the whole system would be asymptotically stable. So for this system also it is asymptotically stable, and for this system also it is asymptotically stable. But it does not say, actually this is in fact only necessary condition. In fact, if I have a Gj omega crossing this line, we cannot say that whether it is unstable or not. Okay, so we have to go for other analysis. But if it does not cross this line, then we can definitely say that the system is asymptotically stable. Okay, so now this was for the linearity lying within the sectors K1 and K2. Okay, so I have so we will extend it to the other conditions also. If I have the nonlinearity lying within the sectors K1 and K2. So now we will try to shift. That was the first case, lying within K1 and K2. So we got this disk here. So it should not either encircle it, and if at all it encircles, then there should be m number of poles on the right of the imaginary axis for the open loop system. Okay, so now if we try to, this is minus 1 by K2 and this is minus 1 by K1. Okay, so now if I try to push this K2 to this infinite line, what happens is that if I try to push it to the blue line, what happens is that K2 would be pushed to this line. Okay, so if I try to push it here, this circle goes on increasing and it would finally reach this point. Okay, so then this becomes a forbidden region. Okay, so now if we have another thing like this is for K1 and K2 greater than 0. This is for 0 lying between K1 is less than less than K2. So we will see another condition here. So for K2 can go up to a maximum of infinity, so it will be just going on increasing the circle and on. So it is definitely greater than 0. So this comes under this condition, and it is just like encircling this disk K1, K2. Now let us try to push this K1 down and then see what happens to maximum, what we can push it. As we go on increasing K1, what happens to the system as we go on increasing K1? So let me put K2 over here, minus 1 by K2 here itself, because here or here it doesn't matter. So what happens to K1 if I try to push K1 downwards? What happens? K1 decreases. When K1 decreases, what happens? This is being pushed to this line. Okay, so what happens? The curve goes on increasing. The initial curve was like this, something like this. This was the forbidden region initially. So I had a minus 1 by K1 here. So if I go on reducing K1, so what happens? This curve goes on increasing. The circle goes on increasing its diameter, and then it goes on increasing. As when K1 goes to 0, what happens? This would be going and touching the infinite point. That means this would be just like a line. This would be just like a line. So this whole area becomes a forbidden region. This whole area becomes a forbidden region. So if you look at the real part also, we can see that what we wanted was a real part of 1 plus K2 into Gj omega divided by 1 plus K1 into Gj omega. So if K1 is equal to 0, so we have 0 equal to K1. Okay, 0 equal to K1, and K2 is less than K2. Okay, 0 less than K2. Okay, in this case what happens is that we need to check only real part of 1 plus K2 into Gj omega greater than 0. 1 plus K2 into Gj omega greater than 0 means that Gj omega has to be greater than, that means the real part of Gj omega should be greater than minus 1 by K2. Minus 1 by K2. That means it should be, that means if I have a Gj omega, the Gj omega curve should not cross this minus 1 by K2 line. Minus 1 by K2 line. So this real part of Gj omega should be on the right of this minus 1 by K2 line for asymptotic stability of the system. Okay, so now we can go to the third condition also here. Third condition here. So what would be the third condition? So I go on reducing. So K1 has come here. K1 is here for the second condition. So K1 has reached the 0 line here. So K1 is being shifted still further. Is being shifted again downwards. Okay. So if K1 is again shifted downwards, where can K1 come here? K1 can come to the third quadrant, fourth quadrant here. So K1 can be shifted still further. That means from infinity it is again being pulled back. It is again being pulled back. So if K1 is being shifted to downwards, that means this K1 is actually the slope, right? So if I have a line like this, it is positive, and if I have a line like this, it is definitely negative. So K1 becomes negative, right? K1 becomes negative. So what is the condition that I can write here? I can write here the third condition is K1 lying between K1 is less than 0, less than K2. Okay, K2 is always positive. I am taking K2 as always positive, but K1 is less than 0. So K1 is being pushed still further. So that means what we can see, if you can imagine properly, you can see that this has been pulled here, and it comes back to this part. Comes back to the positive part, and it slowly approaches, because as it goes on increasing from 0, decreasing from 0, it approaches from minus infinity region to this part. Minus infinity region to this part. So this part will be forbidden, and slowly if you look here properly, this was a minus 1 by K2 which was forbidden. If K1 was 0, this part was forbidden. Okay, that means Gj omega should not cross this part. Okay, so now if this K1 is being decreased further, and it is trying to be negative. trying to be negative. So when it suddenly crosses a zero line, it comes from this point. So this part definitely becomes forbidden. Okay, this part becomes forbidden, and it slowly converges to when, so that means K1 is approaching like this. So slowly each part becomes forbidden, then it becomes a curve like this, circle which is being forbidden. So these parts become forbidden, and then slowly, if for example if it approaches minus 1 by K1 here, minus 1 by K1 is definitely positive, so it would be 1 by K1 here. Slowly we will get a disk here which is the safe region. So all other regions are unsafe. Okay, all other regions are unsafe. Okay, so what does it say now? If I have a nonlinearity lying within these two sectors, then we can say that if the GJ omega plot is within this region, then the system would be asymptotically stable. Okay, so this is about the circle criterion. So we have only 3 conditions for the circle criterion. Only the understanding, it may take some time for you to understand how it comes to this level. Only thing is that we have 3 conditions here. Here the first condition, what it says that if the nonlinearity lies within K1 and K2 sectors, and K1 is positive and K2 is positive. Then we have a disk here, we have a disk here, this is K1 K2 disk here, and the GJ omega should not cross this line. Okay, should not cross this curve, or if at all it encircles, it should encircle m number of times equal to the number of open loop poles. That means m number of times in the counterclockwise direction. Okay, so now we if I have another condition here, if this is the another sector that we have, that is K1 is pushed to 0, and I have this sector condition here, that is I have K2 here and K1 here. This is K2 and this is K1. This is K1. So the nonlinearity is somewhere here, somewhere lying here. Okay, nonlinearity is somewhere lying here. In that case, what can we say? Then we can say that this GJ omega plot should not cross this line, should not cross this line. Okay, so now the third condition is if I have K1 as still negative, so I have the nonlinearity lying within 2 sectors K1 and K2 like this. This is K2 here, and K1 is negative, so I have a nonlinearity lying within the sector, something like this. I have some nonlinearity lying like this. Okay, some kind of a nonlinearity lying like this. Then we can say that the whole system would be stable if GJ omega plot lies within this circle. Would be asymptotically stable if GJ omega lies within this circle formed by this 1 by K1 and minus 1 by K2 points. Okay, so this is about the circle criterion, and suppose I will give we will do problems based on this in the next class. On Thursday we will do that. So but now you try to understand the concept here. So this is the general statement for the circle criterion for the scalar system, which transforms it to the analysis through Nyquist plots. Okay, so we have this system here, and it is a minimal realization which says that the system is controllable and also observable, and we have a feedback within some sector K1 and K2, some sector, and we are having different conditions. This is first condition we had seen, this is the second condition, and this is the third condition. Okay, so it you can just go through that. That means the Nyquist plot does not, if I am having within this sector, that means we can draw it here and see this is K1 and K2 sectors, this is K1 and K2 here, and for this condition here, this is the first case, and this is the second case here. For the second case, so for the second case here, I have only K2 here, K1 is this line, K1 is this line, and the nonlinearity lies within these 2 lines. For example, for this case, you can think about some nonlinearity of this form, for which you know you have some nonlinearity like this, something like this. some saturation kind of nonlinearity. So this we can say that this kind of a nonlinearity lies within K2 and this 0 line. Okay, we can say that this lies between K2 and 0 line. So easily we can come to a conclusion for Gj omega plot. Okay, for this kind of a nonlinearity, it is quite easy. Okay, so now if I have another nonlinearity lying between another two sectors, this is K2 and this is K1, then we can we come to the conclusion that the Nyquist plot of Gj omega should lie to the interior of the disk D of K1 comma K2, and that means that is quite interesting part. From here it should not be inside the interior, it is slowly coming to the interior. Okay, so the forbidden area was small here, and as we go on increase the nonlinearity towards the positive side, what happens that the forbidden area becomes larger here. It becomes larger and larger here. Here the forbidden area was smaller because we had a small sector here. Okay, so this is about the circle criteria. This is a theorem which states that what a circle criterion is. Okay, so this is about the understanding of circle criterion. Okay, so for detailed explanations you can look at Khalil text chapter 7 section 7.1.1, and also especially very good lectures by Professor Harish K. Pillai from IIT Madras. You can look at it. Okay. This is about the theorem on circle criterion. So we will do definitely the problems based on this in the next class. Okay, thank you.